I have a demonstration that I'm going to start here, and in a couple slides we're going to get to it. But I want to raise the temperature of some water here, and I want to add energy to it and raise some water. Now what I have here is ice water. I've got some ice cubes in water, and I've got a temperature, a thermometer on it. What should the temperature be of ice? 0 degrees Celsius, okay? And we're going to raise the temperature. We're going to add some calories, add some BTUs, add joules of energy to this in order to get the water to increase in temperature, okay? So we're going to melt the ice and heat up our water and turn it to steam, okay? I have here a alcohol burner. This is just a little old-fashioned fuel source for the classroom. So I have a flame here. This is in a paper cup, and I'm just going to put this flame under my paper cup, and we're going to heat our water. We're going to melt our ice. Okay? So we'll let that be going while we talk, and we'll come back and check on it periodically as we try to boil our water in this paper cup. Okay. We'll see if it catches on fire. Let's say you're melting chocolate, or let's say you're making candles and melting wax. Chocolate and wax will easily burn, either way. So what do you do when you're cooking? Have you ever done that? You use a double boiler. You use a situation where you've got a pan, like say you might have your chocolate to melt or your paraffin wax to melt, but you put that pan into another pan that has water in it. And then you're going to heat this up. There's our flame. Why would you heat over water instead of heating this chocolate or wax directly on the heat element? More important than just equally distributing heat is that this is never going to get hotter than the boiling point of water. The water will stay at 100 degrees until the water is gone. Why is our paper cup here not burning? Our water is boiling. Why is the paper cup not burning? Because the temperature of this cup is not going to go over 100 degrees until all the water is gone. So if you have foods that you want to keep, you don't want it to get too hot. You don't want to get your chocolate too hot. Put it in a situation where it's over water, because the water will make it stay, so it's only going to go to 100 degrees. Now, if the water boils away, as soon as the water boils away here, if I have an empty cup and I put it over a flame, what's going to happen? The flame would burn. And some of you were nervous because you know that you put paper, this is a paper cup, over a flame, and it's just going to catch on fire. The reason it's not catching on fire is because it will not get over 100 degrees until the water's gone. So that's the whole basis behind double boiler cooking. It's also the basis behind, say, putting, when we have like nuclear power plants and you've got really hot metal rods and you've got them underwater. Because if they're underwater, the water's not going to get too hot. If the water goes away, the amount of that metal energy, that metal temperature could go higher, and they call that meltdown. You're afraid of meltdown or the China syndrome or whatever. You'll get metal melting, but it will never melt if you can keep it underwater. So we've got cooling ponds and cooling chambers in nuclear power plants. So the energy is heating the water, and so we're ending up using steam as an energy source, but it's not going to get hotter than 100 degrees unless the water disappears. Just like your body temperature maintains a certain temperature until the water's gone. When you're dehydrated, it's like a dehydrated cup. The temperature can rise. And you could get here our water, once the water's gone, then the temperature would make it to the flash point, the burning point, ignition point of paper. Question?
I was going to ask if the idea is to have the water below it to keep it the temperature of the water, like with the double boiler. So when you're steaming food, you're using the steam though, not the water to cook it, right?
Now, when you're steaming food, like if you have a basket that has holes in it so that the steam comes up, then you want the steam, and because why would steam be better at cooking vegetables than boiling water? Steam is hotter. It's not hotter as in temperature, but it's got more energy. So cooking, just like a steam burn is more severe than a boiling water burn, steam is going to cook your vegetables faster than boiling water would cook them because it inherently has more energy in it. The other reason for cooking vegetables with steam, and probably the reason that's more important than the speed of the cooking, is the fact that your water-soluble vitamins don't just dissolve into the water. And they're going to cook, and you're going to keep more of your vitamins in your vegetables than having them just dissolve into the water. So that's the more nutritional value of steam cooking. But it will cook faster if it's with steam. We use autoclaves, sterilize surgical equipment, and you use steam. Now, we'll talk about this when we get to the next chapter, and how you can make steam even hotter. Steam has more energy than boiling water, but if we change the pressure, we can even get the steam to have more energy. So stay tuned, we'll do that next time.